distributions. Last session, we discussed the normal distribution, and let me remind you again about the normal distributions. Each day, I remind you for the previous session, and by just attending my class, I'm sure you should be able to make at least 80% of the questions. So the normal distribution is the most important theory distribution. We have the theory distributions and the empirical distributions. We have the theory distributions. Let me write it down. If you have your data, from the data you may calculate your empirical distribution, or we can call it also what? The experimental distribution. Experimental, or we can call it also equal to experimental, equal to observed. That the data we have, which we have observed, and we have the theory distributions. Theory distributions, okay. The theory distributions, in the theory distributions, you have a formula, you have a function. On behalf of that function, you go and you calculate, you draw a distribution, a curve. And the Gauss distribution, or the normal distribution, is the most famous and most commonly used in medicine. The rule for the Gauss distribution was between mean and one standard deviation, plus and minus one standard deviation. We have 68% of the cases. Between mean and plus minus 1.9 standard deviation, or we can roughly say 2 standard deviations. We have 95% of the cases. That's very important in medicine. In medicine, we usually take the 95% of the cases as normal, and above and below 95% we regard as abnormal, high or low. Therefore, we have to know that the mean minus 2 standard deviations and mean plus 2 standard deviations, in between these, we have 95% of the cases. If you have your empirical data and you want to convert it into standard normal distribution, you take the Z formula as it is shown here, which is the measurement x minus x bar or mu divided by standard deviation. But there are other, maybe hundreds of theory distributions invented by other researchers, by other scientists. Among those, a few are very important and not as important as normal distribution maybe, but they are very commonly used in medical practice. And these are the T distribution. Let me write it down here. So the other theory distributions, we have the normal distribution, or the Gauss distribution. Then we have the T distribution. What else we have? We have the chi-squared distribution. The chi-squared, or we show it also as the Greek letter chi. This is the Greek letter chi, chi-squared. What else we have? We have the F distribution, the log normal distribution. The F distribution. F distribution, and the log normal, And then we have to distribute these discrete probability distributions such as binomial and the Poisson. Binomial and Poisson. So if you have understood the normal distribution, the Gauss distribution, if you understood this concept of normal distribution, it is very easy to understand also the others. Just the formulas are different. Just we have different formulas in the background. Do you remember which variables were included in a normal distribution? What are the parameters defining the normal distribution? What do we know to calculate the percentage in a normal distribution? We need to know
A mean and standard deviation.
the mean and standard deviation. Very good. Thank you so much. I feel very bad that students who answer my questions straightforward, so they don't score high in this exam. I hope you will compensate. The mean and standard deviation. So the formula of the density, probability density distribution of the normal or the Gauss, it includes the mean and standard deviation. For the t distribution, let us see the t distribution, what it is about. It is invented by a scientist called Cosset. He's Italian, maybe. And the parameter that characterizes the t distribution is the degree of freedom. Okay, what is it? The degrees of freedom. The parameter that defines the t distribution is the degree of freedom, df. Degree of freedom is simply expressed as n minus 1. This is the degree of freedom. In another course session, I will explain you why it is n minus 1. But now, for this time, you just can memorize it. Huh? If you know the number of people in your sample, you can easily calculate the probability or the area under the curve in the t distribution. It is called the degree of freedom, n minus 1. Okay, its shape is similar to that of the normal distribution, but it is more spread out with longer tails. And if you have high number of participants, it approaches normality. As the degree of freedom increases, which means if you increase the degree of freedom, you increase the number of participants, the sample size, then the shape becomes normally. Let us see in this graph here. It is very beautifully depicted here. You see, we have a t distribution with different normal degrees of freedoms. Here, the degree of freedom is 1. In this, you see, it is 1. You have a bell-shaped curve, but it is more spread out. If you have a degree of freedom 5, it is becoming a little bit taller, and the tails are smaller. You have smaller tails. If you have a degree of freedom of 50, this means 51 participants. If you have 51 participants, you see the curve doesn't change a lot. It changes a little bit. Between 1 and 5, there is a big change. Between 5 and 50, there is very small change. And between 50 and 500, there is a change you cannot see by eye. It is very, very small change. And the lines look like they are superimposed. Did you get what I mean? the parameter defining the t-distribution is the degree of freedom, which means the number of participants. And as you increase the degree of freedom, your distribution becomes very close to the normal distribution. And after 50, or around 50, let's say 30, you may say, or 20, because in 20 and 30 will be also very close to this dotted line here. After 30 or 50, you will have almost normal distributed, almost the same probabilities, same values as it is in the normal distribution. This you should keep in your mind. A t-distribution is very close to the normal distribution if you have high number of participants. Okay. Then the chi-square distribution, it is characterized by the degree of freedom. The chi-square also is defined by the degree of freedom. Degree of freedom again here. But this chi-square distribution is more used for particularly useful for analyzing categorical data. You already know that the chi-square test is applied for categorical data. And if you have categorical data, you will have cross tables like this here. You will have cross tables. Just I'm making to give you an example here. Males and females you have in your in your study, let's say, and you're asking about smoking status, smokers and non-smokers. This is a cross table where you have categorical variables. Two groups. How many groups we have? Two groups, males and females. Two groups. How many categories we have? How many categories? Two categories. Two categories. So 2 by 2. And the degree of freedom in a chi-square is the row minus 1 multiplied by columns, number of columns minus 1. So row minus 1 multiplied by column minus 1. Okay, then column number of columns here is 2, and number of rows here is 2. So 2 minus 1 is 1, 2 minus 1 is 1. Here it will be 1. We have a degree of freedom. If you have this kind of table, it means you have a degree of freedom of 1. Let us look to the chi-square distribution. If you have a degree of freedom of 1, you will have this kind of curve. But as your degree of freedom increases in chi-square, which means you need to have, of course, more cases, then again here, your distribution is approaching normality. It becomes a bell-shaped curve in a chi-square distribution. The F distribution is a proportion. Let us read about the F distribution from the book. Where is F here? It is skewed to the right. It's defined by a ratio. It is a proportional ratio. The distribution of the F distribution is the degrees of freedom of within and between, and it is used for ANOVA, the analysis of variance. So the parameter defining the F distribution is the degree of freedom between and within. Between divided by within. Why between and within? Because in ANOVA, you have more than 2 groups and a numerical variable. So if you have more than 2 groups and you measure the numerical variable, you will have a variation between the groups and of course also a variation in the measurements within the groups. If you divide this degree of freedom of these two, you will have the F distribution. So if I ask you in the exam, what is the parameter defining the F distribution? It is the degree of freedom between and within. It is a proportion, or it is a ratio defined by a ratio. Okay? Ratio. Okay. And the log normal distribution means you have a skewed distribution, skewed, but normalizes, normal after log, after logarithmic transformation. And in the next session, we will discuss what is about log transformation, after logarithmic transformation. On the other hand, the log normal distribution is skewed to the right, and it is the probability distribution of a random variable whose logarithms on base, usually on base 10, follows the normal distribution. The last two important distributions used in medicine are the binomial and the Poisson distribution. In a binomial distribution, you understand from the name binomial, bi means two. Huh? You have success and failures, two options. A variable with two options, yes and no. Success and failure, just like throwing a dice, or looking, for example, in medicine for the success or failure after in vitro fertilization, IVF. The two parameters that describe the binomial distribution are the n, the number of individuals, and in the sample, and the mu, the true probability of success of each individual. So it is the n and the mu, which define the binomial distribution. The n and mu. A Poisson distribution is used for discrete variables, for counts, the number of events occurring, such as the number of people discharged daily in a hospital, which cannot have decimals. It is full numbers. Okay. And the parameter that describes the Poisson distribution is the mean, the average of the counts. Okay. If you have a Poisson distribution, the mu, the average. So that's enough, I believe, for the theory distributions. If you repeat, we have here 2, 4, 6, 7 types of theory distributions with different formulas. I'm not expecting you to memorize the formulas of the theory distributions, but I am expecting you to know which parameters are included in these formulas, which you should know to calculate the probabilities. And most importantly, in a normal distribution, we need to know the mean and standard deviation. For a t-distribution, we need the degree of freedom, n-1. For a chi-square distribution, also we need the degree of freedom. But the degree of freedom here in chi-square is, because it is categorical variable, is calculated different than for the t-distribution. If you have a F distribution, we need the between and within the ratio to calculate the ratio, to know the ratio. And if you have a log normal distribution, it means it is skewed to the right, but becomes normal after log transformation. If you have a binomial distribution, it means you have two options, yes and no. And counts for number of discrete values, such as number of discharged people, we benefit from the Poisson distribution. Okay, what time is it? It's time to have a break.
Yeah.
Okay.
10 minutes.
Let us make 10 minutes break, and then we will come back and discuss transformations. I will not go anywhere. I am here. If you want to discuss with me something, or if you want to keep reading the exam questions, we can do it. Or if you want to repeat something. Evet. Abdullah Kasimov, how was your exam?
It was awful for me.
And why was it awful?
I don't know. I think I wasn't prepared enough for the exams because.
Thank you. You are honest. You don't say the questions were too difficult. Huh? You don't.
Yeah, but it was difficult because I wasn't ready enough.
Okay? Are you attending the classes?
Yes, I'm attending the classes, but sometimes I'm not listening.
Yeah, sometimes not listening. Yeah, because I believe and I insist actually, not just believe. If somebody listens to my class, he should be able to answer at least 70% of the questions. If you listen carefully, and if you ask what you don't, once you don't understand, you should be able to answer. Yeah, but okay, then for the next exam, I hope you prepare. Why you didn't prepare?
Because I don't know how to explain. Many subjects.
You are lazy? I don't think you are lazy. If you are
No,
medical
not
students,
lazy.
you are not lazy.
It was a lot of information for another subjects, lessons.
Yeah.
That
was my guess. You studied, all of you studied physiology. I know that.
Yes.
Dr. Kenan, this is his fault. Okay, so he should come and clear this. Some of you, I know they had internet connection problems during the exam, but for this, there is nothing to do. You should maybe have alternative options for internet, but if it is that there is no internet in the whole country because of bad weather conditions or something, you cannot do anything. It's 10 minutes. I don't know how to spend this 10 minutes because I decided to wait in front of the computer. I don't need to do anything. Let me open the exam and read some other questions, try to solve some other questions, especially this kind of questions where I give you a paragraph from a text, like here, a statement from one scientific article. And what I ask about it, which of the following statements are correct for the above statement? Comparable hemoglobin A1C reduction was observed with a mean plus minus standard deviation change from baseline to 32-week endpoint of 0.9 plus minus 1.1% in the vildagliptin group and 1 plus minus 1.3 in the glimepiride group. These are two medications for diabetes. I don't know exactly what they what are called in the market, and maybe Dr. Azamat knows. And they measured hemoglobin A1C. These are oral antidiabetics, aren't they, Dr. Azamat?
Yes.
Yeah, these are oral antidiabetic medications. I know just they are oral antidiabetics, but nothing more. I don't know their dose or how they are used. So they measured hemoglobin A1C, which is a very important indicator in diabetes, with the mean standard deviation. Here is the mean and standard deviation. Standard deviation. Mean is 0.9, standard deviation 1.1. Which of the following statements are correct? The variable of interest is categorical. Is it categorical, hemoglobin A1C? It is measured from the blood. If it is measured from the blood, I told you, almost 100% it is numerical variable. Only parameters showing the spread of data are given. The spread. What were the parameters showing the spread? The standard deviation, the variance, the percentiles, minimum, maximum. Yes? Only spread parameter? No. We have also the mean. You see, mean and standard deviation. But this is also not correct. The mode is 0.9. There is nothing about the mode here mentioned. The standard deviation is -1. Standard deviation is 1.1 and 1.3. And it cannot be minus, by the way. This data has most probably a normal distribution. We assume that it has a normal distribution because they have given the mean and standard deviation. If the authors have presented mean and standard deviation, we can assume that it is normally distributed. Okay, this was a maybe more difficult question, but we have solved similar ones during the course. Here is a text from a study, Canadian family physician. And the title is Adherence to Antihypertensive Medications Among Family Practice Patients with Diabetes Mellitus and Hypertension. How many of the variables given in the results section are numerical? So I want you to be able to recognize the type of variables. What kind of variables do we have here? The average age. Age is a variable?
Numerical.
It's a numerical.
Time,
Okay.
duration.
Age is numerical. 1.
Time of duration.
51% of the participants were men. Men, sex. Is it a numerical? No.
No.
43% of the patients had diagnosed diabetes mellitus for more than 10 years. So, being diagnosed diabetes, is it numerical variable?
Yes.
No, it is categorical. Are you diagnosed diabetes for more than 10 years? Yes, or the answer of this question is yes or no. Huh? If you give the percentage, 43%, if you give the percentage, it is a categorical variable. We don't give percentage for numerical variable. For numerical variables, we give the mean and standard deviation or median. If it is a numerical, the percentage presented, it means it is a categorical variable. and 49% had a diagnosis of hypertension. Having a diagnosis of hypertension, yes and no. Again, the percentage is given. It's a categorical variable. 89% of patients had some form of medical insurance. Having a medical insurance, is it categorical or numerical?
Categorical.
Of course, that one also categorical. If you have this question, and it is present, they present the percentage only for categorical variables. All patients had seen their family physician providers at least once within the past year. Have you seen your family physician? This is the question, a study question. Have you seen your family physician within the past year? The answer is yes or
Yes
no.
and no.
Yes or no. Is it categorical or numerical?
Categorical.
Categorical. 70%, 77% of patients reported high adherence. Adherence. And it is presented as percent. Also categorical. So the only numerical variable measured here is what? The average age.
The
The age. How many of the variables given are categorical? So the rest are categorical. Sex, 1. Then diagnosis of diabetes mellitus, 2. Then diagnosis of hypertension, 3. And then having medical insurance, 4. And seeing their family physician, 5. Aha. Oh, Dr. Azamat.
Yes.
Is it 6? You see?
Yeah, I chose 5, but it was incorrect.
It wasn't correct, so it should.
Yes.
Okay, let us revise this. Dr. Azamat, this question should be rescored. Huh? Maybe they will get 5 marks extra, all the students. Okay, can you take a note and take care of that?
Yes.
This question number 23. Probably the options, we have a problem, an issue with the options. You have chosen 5, huh? And it was not correct.
Okay. I will.
One of the students said.
I believe
Okay.
it.
Yeah, let us revise this. They will get the 5 marks extra, but it will not help much. Instead of 31, it will be 36. I mean,
Some of them will pass.
Maybe some of them will pass.
Because 50 is a.
Okay. So
score.
let me rapidly go through the other questions. Maybe we have some other issues. Which statement is correct regarding the variable mentioned in the phrase 43% of patients had a diagnosis of diabetes mellitus for more than 10 years? Frequency as well as percentage of the variables present. No, only percentage is given. Arithmetic mean is present. No, percentage. It would be better to present a geometric mean. No, of course, this is a categorical variable. It is a numerical variable converted into categorical. Yes, it is a numerical variable, isn't it? You are asking for how long have you been diagnosed with diabetes? For how long means the duration. The duration in years is a numerical variable, but they categorize it more or less than 10 years. More than 10 years and less than 10. They made it 2 options, 2 categories. So this answer should be D. Yeah, we have 24 questions. Okay, enough. May I continue, Dr. Azamat?
Yes.
Now, in this session, we will discuss transformations. Why do we transform? Why do we transform? This I can delete. Okay.
Maybe
Transform.
when there is extreme values.
Yeah, when there is extreme values, especially when there is extreme transformation. Transformation point. Transformation has at least 3 benefits. It is helping to normalize the data. Then it is helping to help with the spread of the observations and normalize the variance, equalize the variances, and also it may be useful to help linearizing the variables. So it has 3 benefits. One, normalizing. Then variance stabilization. Variance stabilization. And third, linearization. Linearization. So transforming data has 3 benefits, but mostly we benefit from transformation to if we have skewed data, as it is shown here in this histogram. If you have a skewed data, you need to and you want to give the mean, because the mean here is not reliable. You cannot present the mean. You may decide to normalize, to transform it, and then it may become normalized. I have copied your scores from the exam here. These are the scores you got from the exam. I copied them here to the SPSS, and I want to draw a histogram. A histogram of the score showing the normal curve. Here is my histogram. By looking to this histogram, by looking at this graph, what can you tell me? Is it fairly symmetrical or is it skewed?
It's acute.
No, it's like symmetrical.
It looks like
Yes.
symmetrical. If
Yes.
there is one guy. I don't. Who was this? Who scored 80?
Kanan.
Huh?
Kanan Ayhan, probably.
Yeah, I congratulate him. Is he here? He is not attending the class.
Canan Ayhan, it's she.
She.
It's a girl.
It's a girl.
I'm
Yeah,
here.
it should be a girl. Canan is here. Yeah, tebrikler Canan. Congratulations. So,
Teşekkür ederim hocam.
ama she is the outlier. You know, you have to throw her out from the class. She's not like the others. So, of course, I'm kidding. What do we do with the outliers? We don't do anything. We keep them. They are very important for us. So, except this 80, the distribution is very fairly normal distributed. And since we have a fairly high number of participants, we have enough number of cases. We have 83 students in this class taking this exam. This one person with a deviation, with an extreme value or outlier is not that important. It is still, as you see, very highly normal distributed curve. You have a normal distributed curve. But if I had skewed more people with higher scores here, like some other students, 90, 100, scoring 100, and or some students scoring more zeros, then this could be a skewed data. If I have a skewed data, one option before doing the analysis is transformation. And transformation literally means doing any kind of calculation using my variables, using my data. What kind of calculations can I do? The most famous transformation is the logarithmic transformation. Logarithmic. Let me write it down here. So transformations, one is the logarithmic transformation. It can be logarithm on the base of 10 or on the base of e, doesn't matter. Logarithmic transformations. Look what happens if you do a logarithmic transformation. If you have a right skewed data, here, and you take the logarithm of the data, it will become symmetrical. This was right skewed, and this is after logarithmic transformation. We don't have a right skewed data here. Oops. We don't have a right skewed data here. We have symmetrical data. Let us do a logarithmic transformation. Compute, I will calculate. I will calculate the logarithm of score. Just I give a name, any name would be appropriate, but I decided to name it logarithm of score. And I will do the calculation logarithm on the base of 10. LG10 is the abbreviation in SPSS. Logarithm on the base of 10 of score, of the variable score. Okay. I should have a new variable here now. You see the logarithm of, and let me increase the decimals. It is a scale variable. You see the logarithm of 50 is 1.7. The logarithm of 40 is 1.6. So if you take the logarithms, the values approach together. They become close to each other. Let us draw the histogram of this logarithm. Histogram of the log score now, this time. Histogram of the log score, and let us see how it looks like. What happened to my data? The central part moved to the right. You see, it was before transformation, symmetrical. After transformation, it is a little bit left skewed. Did you understand? Are you following me? If I apply, then the rule would be, if I apply logarithmic transformation to my data, it will move, the tail will move to the left. Okay, so the rule would be to write, if I write it down, it is useful for right skewed data, this kind of data. It is useful for right skewed data. If I have right skewed data, and if I apply logarithmic transformation, it will become symmetrical. After transformation, it will become symmetrical. It moves the central part from left to the right. It moves to the graph to the right, the logarithmic transformation.
So it means, can you transform our marks like that?
Sorry?
Transfer our mark like that, like we are at the right, can you make it at the middle?
I couldn't understand.
For example, in our result, it shows like it is right skew data. So
Yes.
if we use the transfer, we can make it normalized data.
Yes, very good. Yeah, exactly.
So,
Ex-
so let's do it.
Yeah, but I don't have right skewed data here. I have your scores here are normally distributed. You want to see it have right skewed. Okay, let us try. Let me order your scores. Order your scores descending. Okay, so we have here one friend was 80. Let's say she had 100. She scored 100, and we have here 90. Just I'm trying to make it more skewed, okay? Is it enough to be skewed? I'm not sure. Okay. Let me see. Histogram. Histogram of score. Histogram of score. Yeah. Now it is right skewed. I changed some of your scores. Okay. I have now more students out as outliers here. And let us do the logarithmic transformation once more. Log score 2, we can call it. Log score 2. And let me draw the histogram for log score 2. Log score 2, the new variable. Okay, you see? Phase?
Yes, sir, I can see it.
Okay, it was skewed to the right. It was skewed to the right. I had a long tail on the right. And after logarithmic transformation, I have a fairly symmetrical. It doesn't mean that in 100% of the cases you will have this. You may sometimes have a normal distribution. Sometimes you may, even after logarithmic transformation, you may not have. You see, there was a big gap between the students. So one student scored 100 and another student scored 40. There was a big gap between 100 and 40. Now, the logarithm of 100 is, of course, on the base of 10 is 2, and logarithm of 40 is 1.6. So the gap between 1.6 and 2 is much less. Therefore, it is normal that we expect a symmetrical distribution after logarithmic transformation. The other commonly used transformation is the square root transformation. Square root transformation. Let me write it here. Square root. So square root nasıl yapılıyordu? Square root transformation. You take the square root of the data. Shall I do it for our data? Transform,
Yes.
compute variable. Okay.
Yes, sir.
Square root score. Let's call it square root score. Okay. Arithmetic square root. Where is square root? Here it is. Square root. The square root of score variable. And click OK. Okay. Let us see the histogram of the new variable now. Histogram of the square root Oops, where is it? Oh, how much? I couldn't click OK. Okay, again, the histogram of square root score. You see, again, it normalized. It becomes normal. So this one also used for right skewed. You will understand the point after I show you the other, the next type of transformation. These are the famous transformations, by the way. You can do any kind of transform, any kind of formula you can apply. The next one is the reciprocal transformation. Reciprocal. Reciprocal means 1 divided by your data. And this will also, as it is in log or square root or reciprocal, all these three transformations will do what? They will decrease. They will make the value smaller. If the value becomes smaller, it is useful for right skewed data. Right skewed. The next one is the square transformation. Square transformation. Square. And last one, another one, the logistic transformation. Number 5 is the logit transformation. Logit is for categorical variables, and it is taking the ln, the logarithm on base n, on base e of the probability divided by 1 minus probability. So this is used for categorical. Okay. The others, the 4 above, are used for numerical variables. Which one of them is different? Square is x square. Huh? Which is different? This number 4 is different, isn't it? While all the others, they make a smaller number of our variable. If you take the logarithm of 100, it is 2. If you take the square root of 100, it is 10. If you take the reciprocal of 100, 1 divided by 100 is 0.01. But if you take the square of 100, it becomes greater number, a larger number. It becomes, the square of 100 is what, 10,000?
10,000.
Yeah, it becomes larger. So only this square transformation is useful for left skewed data. Why left skewed? Why? Because it is increasing the smaller numbers. It is making the numbers larger. Just keep in mind, okay? If y is skewed to the left, if y is skewed to the left, the square transformation may help you, not 100%, but may help you to normalize it. It also helps to linearize and stabilize the variance. As in all other transformations, all the transformations help you to normalize, to linearize, and to stabilize the variances. So if I ask in the exam, what is the use, what is the benefit of doing a data transformation? Then your answer should be, the data transformation will help to make my data normal distributed. It may help me to stabilize my variances, and it may help to linearize. Okay? Do we have time? I should show you also this.
We have 10 minutes left.
Okay. That's good. 10 minutes, I can finish. So, as you see here, before transformation, if you have this kind of parabolic curve, and you take the logarithm of it, this is logarithmic transformation, it becomes linear. It helps linearization. If you have too much scattered, too much deviated variable measurements, high variance, and you take the logarithm, the values will get closer to each other, and then your standard deviation or your variances will be less. Here you have higher variance. Here, after transformation, you have lower variance. A similar picture applies for square transform. The opposite applies for the square transformation. In the square transformation, only in the square, by the way, the others, they all decrease the numbers, while the square transformation is used for left skewed data, it increases. Okay, if you have a left skewed, as it is here, shown here, if you have a left skewed distribution and you apply the square transformation, then you can expect that it will become normalized. The same applies for linearization and variance stabilization. The same rules apply also for the others, for logarithmic transformation, for square reciprocal transformation, and you may do any transformation you can imagine. Yeah, I believe that much is enough. In summary, we discussed that we have 5 different kinds of transformations: logarithm, square root, reciprocal, square, and logit. These are the classical transformations. You can do any formula, you can apply any transformation you can imagine to your data, but the classically used in medical research are these 5 different types of transformations. And among them, the number 1 and the most frequently used is the logarithmic transformation. Yeah, I believe that much is enough for today. Can I say bye? Dr. Azamat?
Yeah.
Okay. Thanks for being with
Thank
me
you,
today.
sir.
Thank you, sir.
Come again.
Thank
Come again next week. Take care. Bye
Have a
bye.
nice day.
Bye bye.
See you.
Salam.
See you.